let's get started. So today I will first finish the discussion for 3.3, and since we're going to jump 3.4 and 3.5, I'm just going to hurry on it. So as for 3.5, I plan to just mention it very briefly and let you know what is the key issue over there. Then I'm going to just you folks will be able to read 3.5 all of this. It's too hard for me. And anyone have any idea about how to
Yeah, I have turned off some of them.
Okay, sounds good.
Do you need to turn off all of them?
Yes, this is because I was like the heat flow is coming to my face and I won't be able to breathe.
Heat flow.
For that.
Heat
Thank
flow.
you. Okay, that would be nice. Yeah, because it's getting hotter. Okay, cool. Yeah, so 3.5 is mostly going to be on your own. Okay, so but that will be required. Okay, that will be required in the midterm. I'm going to but 3.5 mostly is about a bunch of technical details about proving some convergence. Okay, I'm just going to let you know what is the key point of that, and I'm going to let yourself to do the verification. Okay, and we should be able to enter chapter 4. Okay, today, but please don't forget that chapter 4 is not going to be included in the midterm, which is going to take place next month. Only include chapter 1, 2, 3. Okay. Okay. So, oh, by the way, from now on, perhaps it's better to change the deadline for homework to Friday, so we folks will have more time to do it. The homework will always be released on Wednesday or Thursday, and will be due on Friday, which means that you will have more than 1 week to do every time. Okay, so yeah, so the rest of the 3.3. So we were talking about the diffusion with a source, okay, which is the question itself is ut minus k uxx, okay, equals to f x t, where this is the diffusion of the whole real line. Okay, so x t belongs to from negative infinity to positive infinity and from 0 to infinity. Because again, I stress it every time that I write it that the diffusion equation is not backward. It's not backward or equals. Okay, and we have claimed that the solution. Okay, so by the way, sorry, the initial condition is also ux0 equals to phi x. Since we're not having any boundary over here, there is no boundary conditions that is involved. Okay, and last time we claimed that the solution to this diffusion equation was a source. What is the source term? The source term is exactly the f over here. Okay, this is the source. Okay, and we also interpreted that the f x t multiplied by delta t will be can be exactly interpreted as the amount. Okay, the amount of materials or mass, okay, or heat entering x, okay, location x, and between t and t plus delta t. Okay, so fxt multiplied by delta t can be interpreted as the mass entering the system, okay, at location x and between the time point t and t plus delta t. Okay, and so fxt is the source term, and we claim that the solution to the diffusion equation with a source can be just as written as the combination, okay, of 2 parts. The first part is that, so my uxt, the first part is that, okay, so again from integration from negative infinity to positive infinity, s x minus y, t, and phi y dy. And this part is the solution to the homogeneous equation, which means that, again, I suppose I don't need to write down again what does it mean by homogeneous equation, what does it mean by inhomogeneous equation, right? Homogeneous equation just means that the right hand side is 0, f is 0, okay? So this is the solution this is the part one, okay? This is part one, which is solution, okay, to the homogeneous equation. Okay, the homogeneous equation. But don't forget, there's also a part two, okay? And then plus the integration from 0 to t, and then the integration from infinity to positive infinity, s x minus y, and also t minus s, f y s dy ds. Okay, this is the part two. This is the part two. And we have successfully demonstrated in the last class that the part two can be, we have the solution. Oh, sorry, we have the part two in our solution exactly because that every time when we are having something entering the system, we can regard it as something that's added up, okay, in the new added up in the initial condition exactly at that time, okay, and we demonstrated this point by discretizing the time, okay, in the last time. So this is, let's say this is t0 equals to 0, and this is okay, sorry, let me just write. This is t equals to oops. So this is t equals to 0, and this is delta t, and this is 2 delta t, 3 delta t. Okay, and this step is k delta t, and finally we're having this is n delta t, which equals to the big T. Okay? And we demonstrated this point by separating this process, okay, by attaching this process onto n plus 1 different time grids. We were supposing that, okay, so initially we had something, okay, which was our phi x, okay, at the very beginning, and we were supposing that the mass entering the system will only converse on delta t to delta t, 3 delta t, and actually in a discrete fashion only on every time grids, which means that over here the amount of mass entering the system over here is going to be f x t delta t, and then multiplied by delta t. And over here, it's going to be delta t multiplied by fx2 delta t. And here, it's going to be delta t multiplied by fx k delta t. So on and so forth. And then we argue that this system can be decomposed into n plus 1 different, n plus 1 independent diffusion processes. Okay, which means that initially I have something. I have my phi x, okay, this is initial distribution of mass entering the system and then going to diffuse, okay, which means that we are going to apply s x minus y and then phi y dy, okay, and the integration from negative infinity to positive infinity, so t. Okay, and after that, so this is the diffusion process that is going to be applied to the initial condition, and for every following time grids, okay, some new distribution of mass is going to enter the system and then going to diffuse. But don't forget that if they come to, so for the new added sources, well, if they are added to the system at a later time, that means that, okay, this part of the distribution of the mass, actually they will have shorter time to diffuse. Okay, that means that okay, when for any at time t, okay, at time t, for any yes, this part, okay, for any distribution entered, let's say at x k delta t, okay, at k delta t, then for at any time point t, that means that the diffusion time it has experienced is going to be t minus k delta t. Okay, multiply by this, and then I suppose this should be dy. Okay, this should be dy, and then dy. Okay, and then if we add all these combinations, if we add all these combinations up, okay, and then finally we are going to again obtain, so summing up when k starting from 1 to n, okay, and finally we're going to obtain this. And taking, of course, and also taking delta t equals to 0. Okay, we're going to obtain the second term in the system again. And today, the first two things that I would like to do is that first, I would like to derive this. So this was actually a rather physical interpretation and deduction. It's not actually and it's not completely mathematically rigorous. Well, what we're going to do today is also not so mathematically rigorous, but it's actually stand on another level of the viewpoint, which means that we will be rederiving, okay, this formula on the viewpoint of the operator, okay, differential operators. And so that's the first thing. And the second thing is that we are going to verify that this equation is indeed the solution to the diffusion equation with sources. Okay, we need to verify that. We need to verify that this is indeed the solution, okay, to the diffusion equation with sources. And that will basically close up 3.3. Well, okay. And another thing is that, and once we understand how to solve the diffusion equation with sources, we'll be able to also deal with the diffusion equation with sources, but only on half the line. Okay, half the real line, not whole the line. Okay, so now that's 3.3. Let's say part 1. Okay, part 1. Rederive the solution. Rederive the solution. Okay. With the viewpoint of operators, well, differential operators. Okay, with the differential operators. Well, this will be a little bit different. The flavor of this one is going to be a little bit different from the last time, because you see, last time what we did was discretizing the space, right? Okay. But now what we're going to do is to discretize. So last time we were discretizing the time. Okay, we were discretizing the time. Today we're not going to discretize the time. Okay, we'll be discretizing the space. We'll be discretizing the space, which means that I'm going to have something like this. Okay. Okay, I'm going to discretize the space. So again, this is the x-axis, this is the t-axis. This is from 0, this is from 0, and this is from the at the beginning, and this is at the end of time. Okay. So now my and that means that I am trying to use, okay, this space split to approximate, okay, the spatial distribution, okay, or a little bit more specifically, my initial condition phi x, okay, initially it was a function on space, but now the space has really been discretized, which means that my phi x, the x is not going to take continuous values, instead it's going to take discrete values. Or in other words, my phi x now can be approximated by let's say a n by 1 vector. Okay, an n by 1 vector. Or my phi, okay, vector is now something like phi 1, phi 2, to phi, let's say phi m. Okay. The index over here 1, 2, and until n. This is the space index. Okay, or to be a little bit more specifically, this is going to be, you see, originally I was having 5x, now I'm having a 5 as a vector, okay? And this entry is going to be my, this entry is going to be my phi 1, my phi 2, phi 3, and until phi n. Sounds good? Again, this is the space, I'm discretizing the space, right? Originally I was having phi from 0 to whatever x it is. Okay. Now I have been discretizing the space, so which means that now my phi is only going to take values on discretized grids. Okay, so this is going to be phi 1, phi 2, phi 3, and up to phi n. So that's good. Also, my u x t, okay, my u x t originally is a 2D function, but now again the space dimension is discretized. So now it becomes a n by 1 vector of functions type. So what does it mean? That means that now, instead of having a 2D function uxt, I'm actually having an n-dimensional function system. So that is to say, I'm having my u1t, u2t, until unt. So that's good. So that means that here u1t. So this is my u1. u1t evaluated as 0, and this single function, of course, is going to evolve, right? And until time t. Okay. So I'm having my u1t and u2t and until unt. So that's good. This is just discretization. Okay. And so this is the discretization of space. Okay. And of course I'm going to have my fxt, same thing, right? My fxt, of course, it is again an n by 1 vector of functions of time. So which means that we're going to have things like f1t, f2t, until fnt. Okay, so this is written as u vector t, and this is written as f vector t. So that's good? Okay, so that's good. And so to revisit our diffusion equation, again, don't forget we were having the diffusion equation was something like ut minus kuxx equals to ft. Oh, sorry, fxt. This was my diffusion equation, right? Okay. And what I would like to claim right now is that, you see, in our first class, we came up with the idea that the differential operator is actually a linear operator. Okay, the diffusion operator is a linear operator, which means that the second order differential operator is uxx. Okay, if approximated, okay, or discretized in space, we will be able to come up with certain linear operator, or linear in our case because it has really discretized. In this case, the linear matrix, okay, to substitute the second order differential operator. Right? So now discretized, because when everything is discretized, okay, in space. If we are discretized in space but not discretized in time, then the differential operator on time, ut, is going to stay. Okay, because again, this time is still continuous. But the space is now discretized. Okay, so no more differentiations on space. Instead, linear operations on space.
Okay, and we haven't gone to the numerical PDE yet. Okay, but well, we show you that actually this is not so. This is not a. This is indeed can be represented by a matrix. Okay, especially when we are getting into. Well, perhaps we not. Well, we will not get into numerical PDE in this class. But I guarantee that we'll discretize. Okay, the first differential operator, the first order spatial differential operator, or second order spatial differential operator. All of these kind of things can be well approximated and legally approximated. Okay, by certain matrix. Okay, by certain matrix. It's just that here we do not specify which matrix it is. I'm just going to say it's going to be a matrix. So instead of the differential operator on space, what we're having for right here is going to be first of all ut. Okay, ut. This is again, don't forget, this is a n-dimensional vector of functions on time. So ut is now written into dut dt. So that's good. Okay. And now you see k uxs. Okay, k uxs. Again, I'm proposing to use a certain matrix to represent the spatial differentiation. As again is linear. So let me just say this is something like AU. Okay, A is strictly an n by n dimension matrix. Okay, A is an n by n matrix. N by n matrix. Okay, then the right hand side, of course, is going to be F. So this again is a reflection of the central thing of this class. Every time we have a PDE, okay, every time we have a PDE and we want to solve it, every time we want to solve it, okay, and if we don't know what to do, okay, then just try to integrate it or rewrite it into an ODE system, okay, because we already know how to solve this type of ODE system. Right? So now, let's see what kind of equation that we have created. My U, again, this is an n-dimensional system, n-dimensional ODE system, okay? And of course, it's coupled. Each dimension is coupled with each other. Okay, so my du over dt equals to AU, and the right hand side is F. Okay, so in your ODE class, what did you do to solve this equation? Or how did you solve this equation? So I suppose certain symbol were actually introduced in your ODE class, which was for the differential operator. For the matrix A over here. I suppose you introduce something like, let's say, e to at, right? E to at. So this can be regarded. Okay, this can be regarded as the operator semigroup. Okay, let me write it down, but not diving that too deep. Okay, so this is actually the operator semigroup. Okay, operator semigroup, because when the t varies, e to at has the power to map whatever it is in the initial condition. Okay, to what's going to happen later. Okay, so this is a semigroup of operator, or this is a semigroup of mapping. Okay, a group of this is going to be a group of operators always sending the initial condition to what is going to happen at a later time. Okay, but I'm not going to dive into this too deep. Okay, all the things that we need to know is that in the AT, okay, it's still an n by n matrix. Okay, in the AT is still an n by n matrix. Okay, and the specific definition of either AT can be written into something like I plus, well, actually just the Taylor series, the Taylor expansion of either, like just follow the Taylor expansion. Okay, following the Taylor expansion. Of either AT when A is actually a number of the non matrix.
But in this case, it's actually I plus at, and then plus a squared t squared over 2 factorial, and then plus a cubed t cubed over 3 factorial, and then so on and so forth. Right? This is the and is there any question about this? Because we didn't really taught this in class. It all depends on if your ODE teacher has talked about this. All good for everyone? Okay. Cool. Now, if I have either at, then I will be able to represent my ut, okay, the solution ut directly equals to either negative, okay, at, and then phi, okay, phi. Don't forget my phi is now an n by 1 vector, okay, and plus the integration from 0 to t, okay, either a and then s minus t, okay, and then f s ds. So that's good. This is the solution of this ODE. This is the solution of this ODE by using the using the operator semigroup for A, okay, or by using the symbol beta at. And another comment over here, if there is any ambiguity over here, is that either negative at, again we said that either at is an n by n matrix, so either negative at is also an n by n matrix, and that is the inverse of either at. Okay, is the inverse of either at. Okay. Is there anything that's unclear at this step? No? Okay, I hope not. Okay. So you see, here what we are having, first of all, is either at, okay, either at, and then second, either a s minus t. Okay? And don't forget, we have been claiming that either at is always what? Either at is always things. That's we call it. That when we are it's always the things that when we are calling it as a mapping. Okay, as a mapping. Always trying to map whatever is happening at the beginning. Okay, to a later time. So I am proposing the following. I'm proposing the following. Let me see. Okay. Let's propose. I'm proposing the following change of symbols. Okay, now change of symbols. Okay. Let me just say that my either negative at. Okay. Let's just say it is something. Let's say my st. Okay. I'm deliberately using the big S over here because I would like to, because I wish you folks to relate it to the source function. Okay, I'm deliberately using the S over here. Okay. And therefore, the either a s minus t can be written as something like s t minus s. So that's okay. Okay. Then I will be able to write the solution ut again into, now it's going to be st phi, okay, and then plus the integration from 0 to t, s t minus s, okay, fs ds. So that's good? Every step is so good for now? Okay. Now, going back to the solution, to the PDE, okay, going back to the solution to the PDE. Don't forget, my PDE is ut, okay, actually not ut, it's actually a two-dimensional function, uxt, which equals to the integration from negative infinity to positive infinity s, okay, x minus y, okay, and then t, and then phi y dy, right? And then plus the integration from 0 to t, and the integration from negative infinity to positive infinity as x minus y, and then t minus s, and then fy s dy ds.
So that's good. Okay, and I'm asking you to relate this S, although they, of course these two S are different S. Okay, this S works in the ODE system. Okay, and it doesn't have any specific meaning actually, because that is going to work for arbitrary A. I was just saying that I'm using my A to represent the diffusion equation. Okay, but A can literally be any matrix over here, and this is going to and this representation is going to stand because this equation, the UT, will still be the solution to the corresponding linear equation. To corresponding ordinary equations. Okay, but the S over here, it carries a specific meaning. It's the source function. Okay, it is what makes our whatever it is that makes our solutions to the diffusion equation. Okay, but if we are trying to get away from this, if we are trying to, let's say, suppose you are like me, you wear glasses, okay, and you cannot look into too much details, okay, on the board. All you can see is that I have some S, I have some T, I have some S, I have some S minus T minus S, okay, and the first term doesn't involve any integration about T, because it's something directly related to the initial condition. And the second term, it relates something that's to T, okay, about an integration of T. And it's also related to whatever on the right hand side is always giving inputting, okay, into the system. Okay, then what we can see is a surprisingly, not as surprisingly, but probably surprising at this at this time, okay, surprisingly well we are able to see, okay, the similarity in the form. Okay, the similarity in the form of these two different type of things. Because don't forget that one is the solution to the ODE system. Okay, and another thing is a solution to the PDE system. Okay, the only thing that they share in common was that, okay, let's come back to compare, right? The only thing that it shares in common was that, okay, so I have something that's involving forward on T. I am having something, a linear operator, okay, another linear, in this case, the linear operator, and in this case, the linear matrix, and I'm also having a source term, in this case, fxt, in this case, the FL T. Sounds good? Sounds good? Okay, so that actually reveals that this type of solution actually has a very high level of generality. Okay, it actually is going to work. It's actually going to work for arbitrary. Okay, it's actually going to work for arbitrary equation. Okay, like ut and then plus, let's say, certain things like L u and then which equals to fxt. The L over here is a arbitrary spatial differential operator. Okay, it doesn't have to be second order. It can be any order, or it can be a combination of multiple different spatial differential operators. Okay, and the corresponding solution to this equation, okay, the corresponding solution to this equation is also going to be something like, okay, uxt that equals to, okay, either negative, okay, well, don't forget here I was using A, right? But A was the matrix. A was the matrix for the ODE. A was the linear operations on a finite dimensional space. Here, my L is a spatial differential operator. It's a linear operator on an infinite dimensional space. So it's good. So in this case, if I could define something that's called e to the negative L t. Okay, I'm not going too deep about what is this. Okay, but suppose I am able to write down such a mapping, okay, e to the negative lt. Then e to the negative lt phi, okay, x, and then plus the integration from 0 to t, and then e to L s minus t, okay, and then f s okay.
e to fs ds. Okay, of course, there are many abuse of notations, but the spirit over here, I would like to unveil is that, okay, as long as everything is going forward, okay, as a linear equation, okay, everything is going forward as a linear equation, and which satisfies the form that ut plus certain linear differential operator, okay, of u, and then we are having a source, and then we're having a source term fxt, okay, on the right hand side. Then, okay, this type of solution is going to stand. Okay, well, we will be always expecting a two parts solution. One part of it is about the initial condition, and this is a mapping, always mapping the initial condition to a later time. And here is another mapping, okay, that is always mapping the source terms, okay, the source terms which are accumulating in the system and always keep evolving in the system, okay, on time. Sounds good? Sounds good. I understand there's going to be a lot. There's going to be a lot of questions about this because there are actually many things that are not 100% clear. But again, let me stress again, it is the spirit instead of the technical details. I want you folks to apprehend with you. Okay. Yes, go ahead.
So for that equation, the second term should have something to do with x instead of only depending on t.
Oh, that's a very good question. Okay, that's actually a slight abuse. Okay, that's actually a slight abuse of the. You are talking about here the fs. Why doesn't have an x in that? Is that what you're talking about? Yes. Okay. This I do apologize for that. This is an abuse of notation because the either LT over here. Okay, this mapping is very likely, okay, to be a convolution, and that convolution is going to. Okay, it's going to get rid of the space dimension. Okay, it's going to get rid of the space dimension. And here, this is again another convolution. This is going to be a convolution containing a spatial dimension. Okay, and you are right about this. You are right about this. So to be a little bit more, so that means that if I am having a, let's say, if let's suppose, okay, if I am having a certain source function. Okay, probably this is a little bit better to accept. If I'm having a certain source function for this equation, okay, but not a source function for the diffusion equation anymore. Okay, suppose I'm having a source function for this arbitrary PDE, linear PDE. Okay, and let me call this source function to be a z xt. Z xt. The reason that I'm using z because it's a it can be regarded as a reverse of S, right? Then what you will be, a more rigorous fashion of writing the solution is going to be exactly from negative infinity to positive infinity, first of all, z, okay, x minus y, t, and then phi y, dy. I'm just trying to copy whatever's happening over here, just representing the big S, okay, to big Z. And then plus from 0 to t, and then from negative infinity to positive infinity, and then z, x minus y, t minus s, f, y, s, dy, ds. Is this better? It is better to accept? Do you feel better to accept this one? Okay. What I am saying is that the either negative LT phi, okay, don't forget, this is L is a differential operator. Either negative LT, okay, is a mapping. Either negative LT is a mapping, okay. Mapping what's happening at the very beginning, phi, okay, to a later time. This is equivalent to this, and this is equivalent to this. Sounds good? Sounds good? Okay, I hope so. Okay, so this is another derivation. Okay, this is another derivation of the solution to the diffusion equation with source, and again, not completely mathematical rigorous, but the take-home message over here. Okay, the
take-home message over here is that, okay, there are two terms, okay, there are two terms in the solution to the diffusion equation with the source. One term is about the initial condition, and another term, this term about the initial condition is essentially a mapping, okay, always mapping what happens at the beginning to what happens at a later time, okay. Of course, because this only depends on what? This only depends on, which means that this term only depends on two things. This term only depends on two things. It only depends on one, okay, what is exactly the initial condition? And second, what is the representation of the dynamics taking place in the system? Okay, it only depends on two things, just like the operator form that I've been written over here. Okay, one, the first thing is the initial condition, and the second thing is a representation of the inertial dynamics. It has nothing to do with the source term that will come later along time. Okay, it has nothing to do with the source term. And the second thing, okay, again, the second thing, it consists of three things. Okay, first of all, f, which is a source that comes in time, and second, which is what will happen to these sources. Okay, how will the inner dynamics evolve these sources on time? Okay, then the third part is the integration. Whatever happens to every pieces of the inputs, okay, and we will going to integrate it on time, because this process, this input process, the source is we have sources on every time, on every time section.
And I hope that's and don't forget that form, okay, that form of solution
Actually comes from an analogy of the ordinary diffusion equation. So that's the big message I would like to send over here.
And well, okay. So before we take a break, that's the second part. In part 2 is the proof. Okay, proof for this. Okay, proof for the formula of solutions. Okay, which means that if I indeed have my UFC equals to this, okay, then we are going to prove that this UFC first of all is satisfied the diffusion equation with the source term. Okay, it satisfies the initial equation, the differential equation, the diffusion equation with the source term, and second, okay, it satisfies the initial condition. We need to prove both in one time. Okay. So, of course, the first thing is that this is my u, so I need to talk about what is my partial u, partial t. Right? What is my partial u, partial t? And let's say for simplicity, okay, let us suppose that my phi x is actually 0. Okay, suppose my phi x is 0. That is because this will help me to this is able to help me to just simply get rid of the first equation, right? And this is something that I am really happy to do. Sorry, the first part, the solution. This is something I'm really happy to do, and actually not that illegal because we already understand what is the effect brought by the initial condition, right? So let's get rid of the initial condition for now, and then we'll be talking about the convergence to the initial condition a little bit later. So at this time, let's suppose my phi x equals to 0. Okay. So my partial u, partial t is essentially partial t, and it's going to be the partial differentiation of the second term in the solution, which is, let me write it down again, okay, from 0 to t, and then from negative infinity to positive infinity, s x minus y, t minus s, okay, f y s d y ds. This is one step, right? Very straightforward. Okay. As I have said many times in this class, okay, we are eligible to switch the order of differentiation and integration as much as we want. My question is the following: can we do exactly the same thing right here? Can I just simply switch the order of the partial t and the following two integrations, and then we'll be happily differentiating the s directly? Can I simply do that?
The point s equals to t has some problem there.
Sorry?
The point s equals to t has some problem there.
The point s equals to t has to be what?
Has some problem there.
Has a problem over here. Why we have a problem over here?
Because you cannot do the derivative of the n.
Okay, so let me put it in another way. If I don't have the second integral over here, if I don't have the integration over here, can I switch the order? Yeah, I can do that. Right? And also, if this integration is on time, but okay, the t is not involved in either end, okay, of the integrand, can I switch the order as I want? I can do that, right? The only issue, okay, that is preventing us to directly switch the order of the differentiation and the integration is exactly that t over here, it takes place, okay, in the interval for 2 times. One time it takes place over here, okay, as the upper bound of the integration. And the second thing, it takes place over here, okay, as partially of the s, okay, as partially of the independent variables of the s, okay. So that means that whenever we are taking whenever that we are taking and differentiation, okay, I propose the differentiation in the following way, okay. So the partial t of something, okay, let's say I'm talking about a partial t. Let's say for let's say a big D t. Okay, this can always be written as a limit when t. You have to okay. You know what is limit, right? Yeah, of course everybody knows what is limit. Sorry, when delta t goes to 0, and then dt plus delta t, okay, dt plus delta t, and then minus dt over delta t. Right, this is the definition of the partial derivative. And every time that when we are not so sure about the about switching order of the differentiation and the integration, okay, this is something that we're able to rely on. Okay, which means that I am now going to write the partial u partial t. Okay, I'm now going to write the partial u partial t as, okay, so the limit when delta t goes to 0 and 1 over delta t, okay, 1 over delta t. Then the first thing is going to be from 0 to t plus delta t, okay, and then from negative infinity to plus infinity s x minus y t minus s f y s d y ds. Okay, this is my b t plus delta t, which is everything. And here, this t minus s actually should be t plus delta t, and then minus s. Okay, here I'm just simply replicating everything over here, but just to replace the t, everything that's related to t plus delta t. Sounds good? Okay, and then minus the original thing from 0 to t, from negative infinity to plus infinity, s x minus y t, and then t minus s and then f y s d y ds. It's going to be this. Sounds good? And then, okay, we are able to separate, okay, the integration into 2 parts. The first integration into 2 parts. Okay? The first integration can be divided into 2 parts exactly because, okay, the
the domain of the integration. It starts from 0 and ends at t plus delta t, but don't forget the second one. It starts from 0 and ends at t. If I would like to combine the first integration and the second integration, then their integrants, their domain of integration, has to fit each other, right? Which drives me to separate the first integration into 0 and t, and then from t to t plus delta. Sounds good? So this now becomes, the first gets into two parts. The first thing is from 0 to t, and then the second thing is from 0 to t plus, from t to t plus delta t. Okay, I'm just simply splitting one integration into two. And the first one, the first guy from t, from 0 to t, okay, I'm just going to combine everything directly to the second part. Okay, to the second part. Which means that here I'm going to have when the limit when delta t goes to 0 and when 1 over delta t, and then it's going to be from 0 to t. This is the combination of the first part and the second part. So it's going to be s, okay, x minus y, and then t plus delta t. This guy, okay, minus s x minus y, and then t. Oh, sorry. This is bad. Probably it's a better way to rewrite everything. Okay. So s, okay, x minus y, t plus delta t minus s, okay, and then minus s x minus y, and then t minus s, okay, and then f y s, dy ds. This is the okay. So this is the this is this guy, and then combined with this guy. So that's good. And then the second thing is the integration from t to delta t, right? And then plus, and then plus of the integration from t to t plus delta t, okay? And s x minus y, okay, t plus delta t minus s f y s.
Professor, it should be that is two integrations.
Sorry?
There's another integration on the space, right?
Oh yes, you're right. From negative infinity to positive infinity, you're right. Here. Yes, you're very right about this. Sorry, I missed that too. Sorry for pointing that out. Okay. So this is from 0 to t, and then from integration from negative infinity to positive infinity. I suppose this is right. Okay. Yes. Thank you. For letting me know. So that's good. Okay. The first thing. Okay. So these, and don't forget. Here I'm having a something plus delta t minus something. Okay. Here I'm having this integration only takes place between t to delta t, suggesting us these two terms can be processed, okay, in a different separately. So when delta t goes to 0, what takes place? What happens for the first term? When delta t goes to 0, what happens for the first term? When delta t goes to 0, this guy converges to what? And don't forget, there's a 1 over delta t. There's a 1 over delta t. Or if we want to see it a little bit more directly, let me erase this 1 over delta t. And here, this is over delta t, and this is 1 over delta t. Again, when delta t goes to 0, what is this? What is this? See, everything is the same except for something. This is delta t over here, right? And take the difference and then over delta t. So this is going to be my partial derivative for s. Right? Okay. So the first, so again, this is the first term. Okay, when we take the limit, when delta t goes to 0, the first term is going to become from 0 to t, and then from infinity to positive infinity. Okay, now partial s, partial t. Okay, and then x minus y, t minus s. okay, and then Fy s dy ds. This is the first term, right? What about the second term? What about the second term? It's when delta t equals to 0, right? And what is the length of the integration? It is exactly delta t, right? It is exactly delta t. So the second term becomes, okay, again, the integration from negative infinity to positive infinity, s x minus y, okay, and then t minus s, okay, f y s dy, okay, and the ds, this guy, the dy ds, the ds over here already goes, because this is the integration from t to the t plus delta t, right? It already goes away. Okay, now the question is, what is my choice of s over here? What is my choice of s over here? What is my choice of s over here? The integration again takes place between t and t plus delta t, right? So that means that my s, okay, is between t and t plus delta t, which means that my s should be very close to t, right? And I'm letting my delta t goes to 0. So this is the limit when s approaches t. This is the s when s approaches t. So that's good? So that's good? Okay. Let's again further process these two terms. What about the first term? What takes place with the first term? So first of all, we have talked about the property of s, right? What is s? S is the source function, right? S is the source function. Now we're talking about the partial derivative of the source function. What's the property of the source function? What's the property of the source function? Source function is the
It's also a solution.
it's also a solution to the
Special initial
it's actually one specific solution.
step.
Okay, but satisfy what specific solution to the diffusion equation, but from what type of initial condition?
A step. Zero.
No, the step function? No, it's not a step function.
Zero left hand side and one right.
No, it's not that. You're talking about the Heaviside function, and that's the q.
Oh.
That's the q. Okay, and s is the derivative of that. Okay. The initial condition for the source function is exactly the delta function. Okay, right. The source is s is the source. S is a source function. It's the solution. Okay, to ut equals to kuxx, and then x0. The initial condition ux0 exactly equals to the delta function. When all the mass accumulates on exactly one point. Okay? So, since my S is also a solution to the diffusion equation, what can I say about my partial S partial T? What can I say about my partial S partial T? What can I say about my partial S partial T? S is a solution to this. If any solution to the diffusion equation satisfy that ut is the kuxx. So S is also a solution to the diffusion equation. So the partial S partial T should be exactly partial as the second order spatial differentiation of S, right? Okay, so this will be exactly, let me say. So that means that partial S of partial T exactly equals to, okay, partial S, the second order derivative, okay, of S on space. Sounds good? Sounds good? Okay, well, so let me write one more step. This is from 0 to T, okay, from negative infinity to positive infinity. So now this becomes, okay, partial the second order derivative of s, and then partial x, okay, and then s, oh, sorry. Okay, and x minus y, t minus s, okay, and f y s dy ds.
Professor, is there a constant k at the
Sorry?
front? Is there a constant k at the front?
Constant k, yes, you're right. There should be a k squared, there should be a k for here. Thank you for picking that up. K over here. Okay. But you see, this is indeed a differentiation, right? But does it have anything to do with the integration? Does this differentiation has anything to do with the integration? No, it doesn't. So again, I am entitled to switch the order of differentiation and integration, and which I'm proposing to move this guy out. Okay, I'm proposing to move this guy out, which exactly this term, the first term, exactly equals to the second order of spatial derivative, and from 0 to t, and then from negative infinity to positive infinity, s x minus y, t minus s, f y s dy ds. So far so good? So far so good? Okay. But what is this? What is this? What is this? You see, I was saying that the initial condition phi is 0, right? So my uxt only contains the second part. My uxt only contains the second part, right? And this is indeed the second part. This is indeed the second part for the solution. Okay, which means that one more step. Okay, one more step. This equals to, again, the second order derivative. Okay, x squared, and this is exactly my uxt. Uxt. Okay, so the first term. Okay, the first term. This guy goes here, and finally goes here. Okay? The second order differentiation, the second order of spatial differentiation of u. What about the other guy? What about the other guy? What about this? What is the limit when? Okay, what's the limit for t minus s as goes to t? What's the limit when of t minus s goes when my s goes to t? 0. Okay, good. Which means that I'm talking about something like. I'm actually talking about something like. Okay, this from negative infinity to positive infinity, s x minus y 0. Okay, and f y 0. Oh, sorry, t, you're right. T, dy. Because s simply replaced by t, right? But what is s x minus y 0? What is the source function? What is the source function s x 0? What is the source function s x 0? We just discussed that, right? My source function sx0 is exactly the delta function delta x. So my source function x minus y0, this is exactly the integration from infinity towards infinity delta x minus y f y t d y. Is that right? And what type? And what property of the delta function have we discussed? The delta function. So this is a convolution. If I'm squeezing, sorry, if I'm fixing the t, if I'm frozen the t, okay, the second term is just a function of y, right? So this is actually an integration. This is actually an integration between delta x. This is actually a convolution between delta x and fx, okay, t. Let's not consider t for now. Let's not consider t for now. So this is just simply a convolution between the delta function and another function, right? What is the convolution between a delta function and another function? What is the convolution between the delta function and the other function? It's always the other function, no matter what it is. It's always the other function, right? So this exactly equals to fx over t. So finally, don't forget there were two terms. Okay, there were two terms in the integration. Okay, sorry, in the differentiation. The first term, okay, was sorry. I missed a k. Sorry, I missed a k over here. I missed a k over here and k over here. Okay. The first term is the k, and then uxx. And the second thing is my f. But where did we start? We started from, don't forget, we started from partial u, partial t. So this basically tells us that we have proved that, okay, ut equals to k uxx plus fxt, okay, to move this to the leftwards. So ut minus k uxx equals to fxt. We have really proved that, okay, this u should satisfy the diffusion equation with sources, okay? The u indeed satisfies the diffusion equation with sources. So let's take a 5 minutes break and then we're going to come back.